It's been 4 decades of a long journey, but now the Voyager 2 spacecraft has finally bid farewell to our solar system.
Voyager 2, one of humanity's most ambitious spacecraft, has once again stunned the scientific community with an extraordinary encounter in the cold, dark reaches of deep space. Decades after its launch in 1977, long past the planets it was originally sent to study, the probe has journeyed into interstellar space, a realm so distant and alien that even light from the sun is dimmer than the stars seen from Earth. As it ventured further into the unknown, the spacecraft registered an event that defied expectations and seemingly bent the rules of known physics. It encountered a region of space that was supposed to be empty, but wasn't. Something was there, something moving, structured, and powerful. Before we start, smash the like and subscribe buttons for more updates. This impossible encounter unfolded beyond the heliopause, the boundary where the influence of the sun's solar wind peters out and the interstellar medium begins. When Voyager 2 crossed this frontier in 2018, it became the second human-made object to enter interstellar space, following its twin, Voyager 1. But unlike its predecessor, which took a different route and encountered a smoother transition, Voyager 2's path has revealed a much more complex and dynamic picture of this edge of the solar system. The spacecraft's instruments, though aging, still collect vital data on magnetic fields, cosmic rays, and plasma density, offering rare insights into a region never directly explored. The anomaly began with a strange series of readings from the spacecraft's plasma science instrument, which measures the density and temperature of charged particles in space. In an area that should have been dominated by a thin mist of interstellar plasma, the probe detected a sudden spike in pressure, an increase far greater than what could be explained by current models. This pressure wall, as some scientists have called it, appeared to be pushing back against the solar wind, compressing it like an invisible shield. It was not merely a local fluctuation. It had structure, persistence, and immense energy. Voyager 2 recorded this pressure boundary as lasting far longer than anticipated, suggesting the existence of a complex and perhaps previously unknown interaction between solar and interstellar forces. At the heart of the mystery is the nature of this barrier. It's not a solid object, nor a classic magnetic field as we understand it. Instead, it's a hybrid, a swirling mix of plasma, magnetic turbulence, and charged particles that seem to coalesce into a semi-coherent structure. To Voyager 2, which relies on data packets sent across nearly 20 billion kilometers of void, this barrier didn't appear instantly, but rather emerged over time as the probe drifted closer. Its instruments noted shifts in magnetic orientation, deviations in particle velocity, and sudden alterations in ambient cosmic ray distribution. These changes pointed to the existence of something fundamentally different from the smooth gradient expected at the solar system's edge. Such a formation was not predicted. Prevailing theories had suggested the interstellar medium beyond the heliopause would be more uniform, dominated by galactic magnetic fields and low-density plasma. The detection of a structured high-pressure region calls into question the assumptions made about the sun's interaction with the galaxy. Scientists now suspect that this boundary is more than a transition. It's an interface, a sort of cosmic skin, shaped by the motion of the solar system through the Milky Way. The interaction may generate turbulence, magnetic reconnection, or even shock-like structures, the physics of which are still not fully understood. One of the most intriguing aspects of the encounter was the way it affected cosmic ray propagation. Voyager 2's cosmic ray subsystem recorded an unexpected dip in galactic cosmic rays, a signal that should have risen consistently after the probe passed beyond the heliopause. This dip indicates that the pressure wall not only exists, but has the ability to deflect or absorb high-energy particles from deep space, suggesting that it acts as a kind of magnetic sieve. The implications are enormous. This layer may play a critical role in shielding the inner solar system from harmful radiation, meaning Earth's space environment is not just governed by the sun, but also by a vast and reactive galactic interface. Complicating the mystery further is the difference between what Voyager 1 and Voyager 2 observed. While both probes crossed into interstellar space, the data they sent back showed dissimilar structures and timings. Voyager 1's passage was more abrupt, with a sharp change in particle detection and magnetic field direction. Voyager 2, however, experienced a gradual transition punctuated by this anomalous pressure region. This suggests the heliopause is not a smooth spherical shell, but an irregular, fluctuating frontier. Just like Earth's magnetosphere is shaped by solar winds and magnetic reconnection, the heliosphere, the sun's protective bubble, might be warped and sculpted by local interstellar pressures, galactic tides, and energetic events far beyond our sight. The impossibility of the encounter lies in the contradiction between expectation and reality. For decades, interstellar space was imagined as a vast, near-empty expanse with a slight background of particles and magnetic whispers. But Voyager 2 has demonstrated that the space beyond the sun's reach is alive with complexity. The interstellar medium, it seems, is not a passive sea but a shifting landscape of forces and structures. And the pressure wall, perhaps a standing shock or dynamic sheath, has no clear terrestrial analog. It challenges everything from astrophysical plasma theory to models of galactic wind interaction. The ramifications extend far beyond planetary science. If similar boundaries exist around other stars, and if they vary in strength and structure, they may influence the habitability of planets and the evolution of solar systems. Voyager 2's impossible encounter also offers a rare, tangible bridge between observational astrophysics and theoretical models. The data captured could reshape simulations used to understand cosmic weather, the flow of energy through the galaxy, and even the structure of the Milky Way itself. These findings suggest the heliopause may function more like a membrane, elastic, reactive, and multi-layered. Magnetic fields, rather than simply extending in straight lines or loops, appear to twist and refract, forming zones of entanglement where particles are trapped or accelerated. This would help explain some of the more puzzling aspects of Voyager 2's journey, including strange particle bursts and fluctuating radio wave signatures detected as it moved through the outer heliosphere. For engineers and space agencies, the implications are more practical. Any future mission beyond the solar system, whether robotic or in the far future crewed, must contend with this barrier. The presence of a dynamic, pressurized region means spacecraft could face unforeseen stressors, energy fluctuations, or particle bombardment. Communication systems, power management, and radiation shielding will need to account for conditions more chaotic than previously assumed. Voyager 2, though not designed for such environments, has held up remarkably well, a testament to the ingenuity of its creators and a valuable proof of concept for interstellar travel. Yet even with all it has revealed, the encounter raises more questions than it answers. Is the pressure wall a permanent feature or a transient phenomenon? Does it result from the sun's motion through denser interstellar clouds? Or is it shaped by magnetic reconnection on a cosmic scale? Could it signal the presence of unseen forces or structures, like interstellar shock waves or remnants of supernovae? The lack of a third or fourth probe traveling in different directions limits the ability to triangulate and map this region. As a result, Voyager 2's single line of data must stand in for a three-dimensional mystery. The scientific community now faces the challenge of reconciling this data with long-held assumptions. Reworking heliophysics to account for a non-uniform reactive heliopause will not be easy. Models must now include variables such as magnetic field heterogeneity, plasma wave propagation, and localized energy bursts. These complexities mirror similar mysteries seen elsewhere in space, such as around black holes or at the edge of solar flares. If the interstellar boundary behaves more like a turbulent fluid interface than a clean cutoff, then our cosmic neighborhood is more dynamic than tranquil. Voyager 2 has turned the edge of the solar system from a theoretical demarcation into a living laboratory of cosmic interaction. The shock-like behavior of the pressure wall hints at energy exchanges on a scale hard to replicate in terrestrial labs. The spacecraft's instruments, although outdated by today's standards, remain surprisingly adept at revealing the strangeness of this environment. Their observations are not just historical artifacts. They are active tools reshaping human understanding of our place in the galaxy. The fact that this encounter happened so late in the Voyager mission, more than 4 decades after launch, makes it all the more remarkable. At a time when most machines would be long dead, this probe is sending back data from a region never before visited, revealing conditions never before imagined. It is as though an explorer, having crossed the final mountain range, expected to find open plains, but instead stumbled upon a storm-churned ocean. The unexpected nature of the discovery lends it a sense of wonder and urgency, reminding humanity that the cosmos still holds secrets close to its heart. This encounter also shifts how we understand the concept of interstellar space. It's no longer just the void beyond planets, but a transitional realm shaped by invisible currents, a place where the sun still exerts influence in subtle, decaying pulses. The boundary between solar and galactic domains is not abrupt, but layered and breathing. Voyager 2 has peeled back one of those layers and found something both beautiful and baffling, a celestial frontier that acts more like a living organism than an inert shell. Looking ahead, the implications of this discovery will resonate through multiple fields: astrophysics, space weather, planetary defense, and the long-term goal of interstellar travel. If every star generates a similarly complex boundary, then each solar system is encapsulated in a unique protective sheath, altering how it interacts with the wider galaxy. The structure and strength of these boundaries could affect cosmic ray exposure, stellar wind propagation, and even the retention of atmospheres on outer planets. In short, the nature of the heliopause may be as important to life as a star's temperature or a planet's orbit. Voyager 2's impossible encounter is not just a scientific milestone, it's a humbling reminder of the cosmos' vast unpredictability. For all the data gathered and all the models built, space continues to surprise. The pressure wall beyond the heliopause stands as a testament to that fact, a phenomenon that both defies explanation and demands attention. Voyager 2, in its slow, silent drift, has touched a cosmic nerve, pressing into the skin of the galaxy and discovering that it pulses with unexpected life. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Voyager 2's impossible deep space encounter? We want to hear from you. Thank you for watching, and see you next time.